This is our home, Earth. Its beauty is unrivaled. It gives us the water that we drink, the food that we eat, the air that we breathe. But as for most things, there is also a dark side. In the wake of climate change, natural disasters have increased in frequency over the past decade. These natural phenomena have wreaked havoc for human civilizations. In 2019 alone, there were over 409 natural disasters worldwide, affecting 91 million people and killing around 10,000 people. Just 4 years earlier, in 2015, it affected 430 million people, more than 3 times that of 2019, and killing over 14,000 people. The average number of deaths and missing people from 2006 to 2015 due to natural disasters occurring worldwide, such as earthquakes, hurricanes, forest fires, and floods, was approximately 70,000. Our goal is to change just that. Hi, I'm Kavya.
Hi, I'm Abi.
Hey, I'm Harman.
Hi, I'm Sagar.
And our project's name is Eagle Eye. Our mission statement is to combine drone automation with cutting-edge machine learning to help assist first responders to efficiently locate and save the lives of displaced individuals during the critical hours after a natural disaster hits.
Okay, with that mission statement in mind, we got to work. So we understand that the current internet infrastructure system can be damaged during natural disasters. That's why we propose a solution that doesn't require any internet. So the way this system works is first the user is going to transmit GPS coordinates to the drone via the drone's Wi-Fi network. Then when the drone receives these coordinates, it's going to fly over to that area and it's going to take pictures of the area. When the drone is taking these pictures, it's going to store these pictures in its internal memory storage. Then the drone is going to fly back to the user and it's going to transmit these photos to the user device. And the user device is going to transmit these photos to the edge server via Bluetooth. Now the edge server is going to run a human detection ML algorithm on these photos, which is supposed to detect people in the photos. If it finds someone, then it's going to send their GPS coordinates back to the user so we can get first responders on the way. Because this project was very large, we had to divide it up into 3 main parts. The first is the autonomous flying. The second was the communication between the middleman, the edge server, and the drone. And finally, the third was the machine learning algorithm. And after all that hard work, we present to you Eagle Eye.
Now we'll look at a full system demonstration. First, we enter in coordinates for the area of interest and get these coordinates from Google Maps. The drone then takes off and will fly through the area while taking pictures. Here's a short video from the drone's perspective. Let's pause here for a second. We can see the 3 different parts of our system here: the ad server on the bottom left, the user device with me in the blue sweatshirt, and finally the UAV, which is the drone. Once the drone lands, the user device detects that the drone has landed and requests for the pictures. The drone then transfers the photos to the user device, which then transfers those photos to the edge server. Let's take a closer look at what happens in the edge server once the photos have transferred from the user device. This is the edge server. We can see on the terminal on the right, what's happening is that it's listening for a command from the user device. Once it receives that command, it runs its script to download all the pictures from the user device. Once it's downloading these pictures, it then puts these pictures through the machine learning algorithm. This is what you can see from the left terminal window. We can see that once the algorithm is done, it'll start deleting these pictures to save memory. It then writes these pictures to an output folder that we're going to view right now. And we could see that in 2 of the pictures, the algorithm detected 2 bodies. Okay, Now let's go back to our system. In the meantime, we attach an envelope to our drone. This envelope contains a message from our first responders. We wait for the edge server to transfer the photos that we got from the machine learning algorithm to the drone. Once the drone receives these pictures, it automatically takes off and flies to the locations of these displaced individuals. Once it gets to the location, it lowers down to a safe area so that these individuals can grab the envelope. The message in the envelope ensures these displaced individuals that help is on the way and that they will be safe soon. That was an overview of the project. Now let's look into some technical details to see how the project really works. Let's start with the drone. We're using a Parrot Bebop 2 drone that we got on Amazon for $200. This is much cheaper than industry drones. The drone comes with an SDK and developer tools so that we can use programming scripts to communicate with it. In our situation, we used Android Studio and Java to communicate with the drone via an app that we created on our user device. Now, we use the Parrot Bebop 2 drone's developer tools plus QGC formatted messages called Mavling messages to make the drone fly autonomously. QGC formatted messages, also called Mavling messages, are simply universally used messages by helicopters, quadcopters, tricopters, or any other UAV to fly autonomously. Here's an example of how a Mavling file would look. Each line is a different command, and each line consists of different parameters. The first three parameters are simply to specify what kind of command it is, whether it's a takeoff command or to go to a specific location command. In this example, the first line is a takeoff command, meaning it'll just tell the drone to take off at the position it is already in. The second line is a command to tell the drone to go to a specific location. And here's where the latter 8 parameters come into play. We can specify what kind of latitude, longitude, or altitude we want the drone to go to. And once we have these Mavling files, we upload this Mavling file to the drone via Wi-Fi. And since we don't have internet during these disaster-struck times, we actually create a unique Wi-Fi connection between the drone and the user device, so they can communicate and transfer Mavling files into the drone. The drone follows the Mavling file as long as it's calibrated and it has a fixed GPS coordinate. And this was one of the challenges that we faced during this part of the project. We have to programmatically fix the drone's GPS as well as calibrate it. After these two things are done, it'll follow its Mavling file and autonomously fly to all the locations that we specify it to fly to. Once the drone flies to its specific locations and comes back and transfers the photos, Harmit now will explain what the middleman of the pipeline does with the pictures.
Now, after the drone has completed its flight plan, it has to transmit the photos it took. First, we fetch the images from the drone's internal memory and download these photos onto the user device. We accomplish this task using the drone's API. When the photos are on the user device, then we send the photos to the edge server via Bluetooth. Now, the issue we ran into was we couldn't program the Bluetooth on Windows or Mac OS operating systems. That's why we had to use the Raspberry Pi. The Raspberry Pi is connected to the laptop through an Ethernet cable, so the laptop can access all the files that are going to be sent to the Raspberry Pi. Another issue we ran into was Bluetooth could only send a specific amount of bytes at a time. That's why before we sent the pictures, we had to divide up the pictures and we had to send each bytes in packets. When the Raspberry Pi received these bytes, then it created the pictures again in its local folder. And after it creates the pictures, it then signals the ML algorithm to start running. Now Sagar is going to go over the details of this ML algorithm.
After the images are sent over Bluetooth from the user device to the edge server, we have a script that detects when images are added to edge server folders and automatically triggers our machine learning algorithm. This ML algorithm will go through every picture taken in that folder and quickly determine if there's a recognizable human in that photo. We use a combination of deep learning and computer vision to determine what objects in the images are classified as humans. If the algorithm has more than 50% confidence that the object it detects is in fact a human, it's going to outline that person on the photo itself with a red box. Once all the pictures have been parsed through, the Edge server sends the images with humans detected out into the output folder. Then, those images in the output folder will be sent to the user device. Additionally, the server will also create an array list of all the photo file names that have humans recognized in them and send them to the user device as well.
Now that the user device has a list of images where the humans are found, the user device will go through each of those images to identify the corresponding GPS coordinates where the drone took the picture. This GPS coordinate is extracted from the metadata in the photo itself. From here, the phone will show the images where the humans were detected, as well as the coordinates to help first responders locate the displaced individual quickly. If desired, the drone also has the capability to fly back out to the coordinates of the identified individual to drop off a marker or necessary supplies like medical equipment and water. This is vital in letting displaced individuals know that help is on the way and aiding first responders to prioritize individuals that might need more assistance.
Now you know the secret sauce behind our project. You know how our technical implementation is done and some of the different features that our project showcases. Going into the future, we'll definitely build on these different verticals and make the project more efficient and include more features so we can save more lives. The solution right now that we have is very cost efficient and very versatile. It's cost efficient because our only overhead cost is really the paired Bebop 2 drone, which is around $200. And compared to industry drones that are over $10,000, that's almost 98% in savings. Our solution is also extremely versatile because you can use it for a range of different issues. For example, amidst the COVID-19 pandemic, we could use our system to deliver critical supplies such as face masks and hand sanitizers to nearby neighborhoods or our neighbors directly. And we could also use our drones to monitor highly dense areas and tweak our machine learning algorithm so that it can detect groups of 10 or more people. Then the drones can alert law enforcement so they could break up these groups, which will promote social distancing as well as limit the spread of the virus. Now Sagar will go into another solution that our system could be used for.
Another problem that Eagle Eye can help address is farming, a $100 billion industry in America alone. The machine learning algorithm can be trained to recognize poorly nourished areas using qualifiers like dark areas or lower density, and notify the farmer to tend to those specific patches of land. Just like before, solutions do currently exist for this, but just not at this low of a price point. The list goes on and on. The overall benefits of doing all the computationally heavy work on an edge server instead of on the drone itself allows us to make much cheaper solutions than currently exist. Eagle Eye's flexibility and capabilities make it an extremely lucrative product if we were to enter the market today.
And with that, we hope you enjoyed our presentation. Thank you.
Thank you.
Thank you.
Thank you.
Thank you for your time, and we hope you share our Eagle Eye vision.